Throughout this chapter, we've been discussing about how the perspective shifted from classical to quantum, right? Classical, where scientists believed most quantities are continuous, they can take any value, to quantum, where they realized that some quantities can only take certain discrete values. So we're going to look at the same shift in perspective in terms of electron movement now. So you have, let's say, a block of metal. The metal, as you know, is made up of atoms. The atoms, again, they have a nucleus consisting of your protons and neutrons, around which you have orbits, and in those orbits your electrons lie and they revolve. So this basic structure we're all familiar with. So now for a long time it was believed that these electrons, their energy, momentum, all of that are continuous, and there were some such assumptions made, and then the idea of quantum came forth, and those assumptions were proved to be false, and new discoveries were made. So that is what we're going to be looking at in the first half of this lecture. So we start with the classical free electron theory. So when classical physics was in force, when people were not aware of the idea of quantum, when they thought everything is continuous, these are the assumptions they had about electron behavior. Valence electrons are free to move about in a volume of metal which is composed of ion cores with nucleus and the rest of the electrons. This is called the free electron gas approximation. And what it says is, you have a volume of metal, like I said, let's say a block of some metal. It is composed of cores with the nucleus, and surrounding it are the electrons. These electrons are free to move about throughout the metal. So let's say you have this block of metal which is made up of 5 atoms. There is no restriction on an electron that it can move around only in the surroundings of the atom it belongs to. This was an assumption. They assumed that the electrons pertaining to all 5 atoms are free to move across the entire volume of the metal. The electrons are not restricted to the surroundings of their parent atom. This was one assumption, and it was called the free electron gas approximation. Why the word gas here? Because they are free to move about like molecules of a gas. So this is a picture we've all been seeing right from high school days, right? The solid, liquid, gas, the arrangement of molecules. And in gases, we say that the molecules are loosely arranged and they are free to move about throughout the volume of the gas. So like that, they assumed the electrons are free to move throughout the volume of the metal. So that was the free electron gas approximation. The electrons obey kinetic theory of gases, meaning energy and average velocity depend on temperature. So if you remember kinetic theory of gases from your 11th standard, there was this formula. Your thermal velocity Vth is given by root 3 kT by m, where k is your Boltzmann constant, m is the mass of your electron, and T is the temperature in Kelvin. So if you substitute that with the mass is generally 9.1 into 10 raised to minus 31, k again is a constant, and temperature generally we take 300 Kelvin, which is, if I'm not wrong, room temperature. So when you substitute those values, you get the average velocity of an electron to be 1.17 into 10 raised to 5 meter per second. So this is, you might be asked in your 1 marks and sort of questions, what is the average velocity of an electron at room temperature, and the answer is 1.17 into 10 raised to 5 meter per second, or 117 kilometer per second. And how did that come about? It came about because of this assumption that we make, that electrons obey the kinetic theory of gases. Now before we move on to the remaining assumptions, one point I'd like to clarify is that I said these assumptions were made based on classical theory, and then when quantum came, some of these assumptions were proven to be false and new discoveries were made. But that doesn't mean every single one of these assumptions is false. Some of them could be true, some were disproved, and later the contradictory proof came out. So we're just going to look at things in the order in which they happened. So just because all of these fall under the topic classical. Please don't assume that everything is false. So yeah, that's your first two assumptions. The third one, electrons move in a uniform potential field generated by fixed ions and have continuous energy distribution. So this means that the potential created by your ions is uniform. There's no change in potential, and the energy is continuous. This is what we almost already know to be false, because that's what we've been dealing with throughout this chapter. Energy levels are discrete. But back then, when classical theory was in force, they thought an electron can have any energy. They didn't know that there are specific energy levels. The electrons move around randomly and suffer scattering due to collisions with stationary ions, leading to instantaneous abrupt change in velocity. So again, you have your core, which is composed of your nucleus and positive charge, and then there are electrons, right? And we said the electron is not going to be restricted to its parent atom. It is going to be roaming around throughout the volume of the metal. So it moves randomly and it collides with the ions, and because of this collision, there is an instantaneous abrupt change in its velocity. Velocity meaning it could be the magnitude as well as the direction. So it scatters. So you look at this picture, this is an example. So these red colored circles are your ions, the nuclei, and your black colored dots represent your electrons. So an electron comes traveling like this, it hits this nucleus and it's deflected to this direction. So you can see the direction changes and the velocity, the magnitude might also change, and this collision is random. That is what the fourth assumption says. Fifth assumption, the mean free time between two successive collisions, and therefore the mean free path is independent of the electron's position or velocity. Mean free time is the average time between two successive collisions. So if this electron comes, hits this nucleus, collision 1, it gets deflected and travels and hits this nucleus, collision 2, and then goes this way. Mean free time is the time taken between collision 1 and collision 2. And mean free path is the distance travelled between collision 1 and collision 2, meaning from here to here. So these two quantities are independent of the electron's position or velocity. That is one assumption. Apart from ion-electron collisions, all other interactions are ignored. What do we mean by all other interaction? There is no electron-phonon interaction. So by ion-electron collision, I mean the electron colliding with the nucleus. So any other type of collision is ignored. Electron-phonon meaning the collision between an electron and a positive charge is ignored. Electron-electron interactions are ignored. Electron interaction with the positive charges are ignored. So basically these were some assumptions which scientists made when trying to study the movement of electrons in a substance. So firstly, the electron is free to move throughout the volume of metal. It obeys the kinetic theory of gases. Its energy is continuous. It suffers random collisions with the nuclei, and because of that its velocity and its speed, magnitude of speed and direction both change. The average time taken and distance travelled between two successive collisions does not depend on the electron's position or velocity, and there might be different types of collisions: collision between two electrons, between an electron and a proton, between electron and a nucleus, between two protons, anything. But the only kind of collisions we will be considering are between the electron and the nucleus. All other kinds of collisions are ignored. These were the initial assumptions.